Tonight, we're embarking on a journey to explore something that might sound straightforward at first, but is actually one of the most thought-provoking and mind-expanding concepts in all of science. We're talking about a light year. Now, you've probably heard this term countless times throughout your life. Scientists throw it around constantly when they're discussing space, the cosmos, distant stars, and faraway galaxies. But here's something that most people don't truly realize, and it's something that I want to help you understand tonight. When you actually grasp what a light year means, when you truly comprehend the distance it represents and wrap your mind around its implications, it fundamentally changes how you perceive the universe around you. This isn't just some big number that astronomers use to sound smart or to make their work seem more impressive. It's a distance so incredibly vast, so monumentally enormous, that it challenges our very ability to comprehend it with our human minds. And by the end of this exploration together, you're going to understand exactly why astronomers absolutely need this measurement, and why nothing else would possibly work when measuring the incredible distances between stars and galaxies. Before we venture any further into this cosmic journey, if you find this kind of deep, thoughtful exploration interesting and valuable, a quick like or subscribe would really help this channel continue to grow. It's such a small thing for you to do, just a single click, but it makes an absolutely huge difference for me and allows me to keep creating this kind of content. Now, with that said, let's dive right in and begin our exploration. Understanding distance in our daily lives. Let's begin with something completely familiar to you, something you encounter every single day of your life. Distance. You understand distance in your everyday life in a very intuitive way. You know exactly how far it is from your home to the grocery store, how long it takes to get to your workplace, what the journey is like to the next city over. These are distances you can genuinely relate to on a personal level because you've actually traveled them. You have a real sense of what they mean in terms of time required, in terms of effort expended, in terms of what you'll see along the way during your journey. Think about a kilometer for a moment. A kilometer is roughly the distance you can comfortably walk in about 10 to 12 minutes at a normal, relaxed pace. These kinds of measurements work absolutely perfectly well for everyday life and everyday situations. If someone tells you that the store is 5 kilometers away from where you currently are, you immediately know roughly how long it's going to take you to drive there in your car. You can picture the journey in your mind with clarity. Maybe you'll pass a few traffic lights along the way. Maybe you'll see some familiar landmarks that you recognize from previous trips. The distance feels concrete and relatable to your human experience. If someone mentions that a particular city is 200 kilometers away, you can plan your trip accordingly with confidence. That's roughly 2 hours of driving time on a highway. You'll want to make sure you fill up your gas tank before you leave. Maybe bring along some snacks for the journey, and perhaps plan for a rest stop somewhere around the halfway point. These distances are human-scaled by nature. They fit comfortably into our lives and our direct experience. We've evolved over millions of years to understand distances we can walk in a single day, distances we can see with our own eyes, distances that matter for survival and navigation in our immediate environment. But here's where things start to get interesting and more complicated. These measurements that work so well in daily life start to become awkward and unwieldy when we begin talking about really large distances that extend beyond our everyday experience. Consider this. The distance from New York City to Los Angeles is approximately 4,500 kilometers. That's still a manageable number to work with in your head. It's about a 5-hour flight on a commercial airplane. People make that journey all the time without thinking too much about it. They cross the entire continent, watching the landscape transform dramatically from East Coast cities to Midwest plains to Rocky Mountains to Southwest deserts and finally to the Pacific coast. The journey is certainly long, there's no denying that, but it's achievable. It's well within human capability and experience. You can imagine making that trip yourself. The Earth's circumference at the equator is approximately 40,075 kilometers. That's definitely a big number by everyday standards, but it's still something we can work with conceptually and wrap our minds around. Early explorers actually sailed all the way around the world, so we know from historical experience that it's possible to travel that distance, even if it takes many months of continuous travel. Ferdinand Magellan's famous expedition took 3 years to circumnavigate the globe from 1519 to 1522, though Magellan himself died during the journey and didn't complete it personally. Modern commercial flights. If you could somehow book connecting flights that went all the way around the planet in one continuous journey, could circle the Earth in approximately 45 hours. The Earth is certainly large from our perspective when we're standing on its surface looking around us, but it's not incomprehensibly large by any means. It's a finite thing that you could, in theory, explore completely if you had enough time and resources, moving beyond everyday distances. But now, let's go bigger and venture into territory that starts to challenge our intuitive understanding. The distance from Earth to our moon is approximately 384,000 kilometers. This is exactly where our normal measurements that work so well for everyday situations start to feel inadequate and insufficient. 384,000 kilometers. That's genuinely hard to visualize in any meaningful way that connects to your direct experience. It's not like driving across your country. It's not like sailing around the world. It's something completely different, something alien to human experience throughout most of our history. There's no road to follow on this journey, no landmarks to pass by and recognize, no rest stops along the way where you can stretch your legs and grab a coffee. It's just distance. Pure, empty distance across the void of space. How would you even begin to travel that far using any conventional means? The Apollo astronauts who made this incredible journey took approximately 3 days to travel from Earth to the Moon using some of the most powerful rockets ever built by humanity. These rockets accelerated the astronauts to speeds of around 11 kilometers per second. That translates to roughly 39,600 kilometers per hour, which is approximately 400 times faster than typical highway driving speeds. Think about that for just a moment and let it sink in. 400 times faster than you've ever driven in your entire life. And even at that absolutely incredible speed, which required some of the most powerful and sophisticated rockets ever constructed, burning enormous amounts of fuel in the process, it still took 3 full days of continuous travel. 3 days of traveling through empty space at speeds no human being had ever experienced before in all of history, just to reach our nearest celestial neighbor hanging in the sky above us. And that's just to reach the Moon, which is the closest celestial body to Earth. The Moon is so close to us that you can see it with your naked eye on any clear night. You can observe details on its surface using just a simple pair of binoculars. It's right there, hanging in the sky above you, a constant companion to our planet. And yet, despite this apparent closeness, it takes 3 days of rocket-powered travel to actually reach it. The distance to our Sunday. When we start talking about the distance to other planets in our solar system, to our sun, to other stars beyond our solar system, kilometers become completely and utterly useless as a unit of measurement. The numbers get so incomprehensibly large that they lose all practical meaning. They become abstract symbols written on a page, rather than distances you can relate to in any intuitive way whatsoever. The distance from Earth to the Sun is approximately 150 million kilometers. Go ahead, try to visualize that distance in your mind right now. You can't, can you? Your brain just sees it as a really big number, an abstraction, but you don't have any genuine intuitive sense of what it actually means in real terms. There's absolutely nothing in your daily life that prepares you for a distance like that. Nothing in millions of years of human evolution prepared us to think about distances this enormous. We evolved over countless generations to understand the distance to the next water source that our tribe needed to survive, the distance to the hunting grounds where we could find food, the distance we could walk in a single day before exhausting ourselves. We can count to a few hundred without too much difficulty, maybe even a few thousand if we really concentrate and dedicate ourselves to the task. But 150 million? That's so far beyond our natural cognitive capabilities that it might as well be infinity for all our intuitive understanding. The Apollo spacecraft that successfully took astronauts to the moon traveled at approximately 11 kilometers per second on average during their journey. At that same speed, it would take approximately 160 days, which is over 5 months of continuous travel, just to reach the sun's distance from Earth. The fastest spacecraft humans have ever built and launched, the Parker Solar Probe, travels at speeds up to 192 kilometers per second when it's close to the sun, using the sun's own gravity to slingshot itself to higher and higher velocities with each successive orbit. Even at this absolutely incredible speed, which is roughly 17 times faster than the Apollo spacecraft that took humans to the moon, the probe still takes many months to complete its carefully planned orbits around our star. And remember, the sun is close to us in cosmic terms. It's right here in our cosmic neighborhood. It's the very star we orbit every single year. It's the source of all the light and heat that makes life on Earth possible in the first place. We see it every single day of our lives. It's familiar, constant, reliable, and yet it's 150 million kilometers away, a distance so monumentally vast that even our fastest spacecraft takes months to traverse it. The challenge of measuring cosmic distances. When we start talking about distances to other stars beyond our own solar system, even the sun's already enormous distance becomes tiny and insignificant by comparison. The sun is our nearest star, and it's 150 million kilometers away. But the next nearest star, called Proxima Centauri, is approximately 266,000 times farther away than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. This is precisely why astronomers desperately needed a different unit of measurement for cosmic distances. It wasn't because they like making things complicated for no reason, and it wasn't because they want to confuse the general public with intimidatingly big numbers. It's because kilometers simply don't work anymore when you're measuring the vast distances between stars and galaxies. Using kilometers to measure distances to stars would be exactly like using millimeters to measure the distance between different countries. It's technically possible, mathematically speaking, but completely impractical for any real-world use. The numbers become so astronomically large that they lose all meaning and context. They stop being distances that we can comprehend and become just numbers, abstract mathematical concepts that don't connect to anything in our lived experience. Introducing the light year. So, astronomers came up with something different, something more practical for measuring these cosmic scales, the light year. But here's what you absolutely need to understand right from the very start, and this is crucial. A light year is not a measure of time, despite what the name might suggest. I know it has the word year right there in it, which makes it sound like it should be measuring time somehow, but it's not. A light year is a measure of distance, pure distance through space. It represents the distance that light travels in 1 year of continuous motion. Now, you might be wondering, why would we base a measurement of distance on light specifically? What makes light so special? The answer is that light is fundamentally special in the universe. Light is the fastest thing in the entire universe that we know of. Absolutely nothing can travel faster than light, according to our current understanding of physics. This isn't just a speed limit that we haven't managed to break yet with current technology. It's a fundamental law of physics that appears to be built into the very structure of reality itself. The speed of light is a constant, unchanging and eternal, the same everywhere in the universe under all conditions. Whether you're here on Earth, standing on the surface of Mars, floating in another galaxy billions of light years away, or somehow positioned at the very edge of the observable universe, light always travels at exactly the same speed. This constancy makes it perfect for defining a unit of measurement: the speed of light. Light travels at approximately 300,000 kilometers per second. Let me repeat that because it's genuinely important for understanding everything that follows. 300,000 kilometers per second. Every single second that passes, light travels 300,000 kilometers through space. This isn't just some rough approximation or a convenient estimate. It's been measured with extraordinary precision, using sophisticated equipment. The exact value, measured to many decimal places, is 299,792.458 kilometers per second. But for our purposes throughout this discussion, 300,000 kilometers per second is close enough and easier to work with mentally. That's incredibly, almost incomprehensibly fast. To put it in some kind of perspective that might help you grasp it better, light can travel around the Earth's equator approximately 7.5 times in just 1 second. In the brief time it takes you to snap your fingers together, which is maybe a quarter of a second, light could circle the entire planet multiple times. In 1 single second, light could travel from New York to Los Angeles and back approximately 37 times. It's a speed that's almost impossible to visualize properly, because absolutely nothing in our everyday experience moves anywhere even remotely near that fast. The fastest thing that most people experience regularly is a commercial airplane. A typical commercial jet flies at approximately 900 kilometers per hour, or about 0.25 kilometers per second. Light travels over 1 million times faster than that. The fastest car ever built by human engineering, the Thrust SSC, reached approximately 1,200 kilometers per hour, or about 0.33 kilometers per second. Light is roughly 900,000 times faster than even this record-breaking car. Even the fastest spacecraft we've ever built and launched into space, the Parker Solar Probe, traveling at 192 kilometers per second at its peak velocity, is still only traveling at approximately 0.064% of the speed of light. It's moving incredibly fast by any human standards, faster than anything else we've ever built. But compared to light itself, it's absolutely crawling along at a snail's pace. Light delay in our solar system. When you turn on a light switch in your room, the light reaches your eyes essentially instantly because the room is so small. The light travels from the bulb to your eye in approximately 10 billionths of a second. That's so fast, so incomprehensibly brief, that there's absolutely no perceptible delay whatsoever. As far as your brain and nervous system are concerned, the light appears completely instantly the moment you flip the switch. But the light did travel through space. It took time to cross that distance. It's just that the time was so incredibly short that you couldn't possibly notice it under any circumstances. When you see the sun in the sky on a clear day, you're actually seeing it as it was 8 minutes and 20 seconds ago, not as it is right now, in this present moment. That's because that's exactly how long it takes light to travel from the sun to Earth across the intervening space. The sun is so far away that even light, traveling at 300,000 kilometers per second, needs over 8 minutes to cover the distance between the sun and our planet. This has a genuinely interesting and somewhat unsettling implication when you think about it carefully. If something dramatic happened on the sun right now at this very moment, if it suddenly changed color or dimmed significantly or even exploded catastrophically, we wouldn't know about it for over 8 minutes. The event would occur on the sun, but the light carrying information about that event would still be traveling toward us through space. We'd keep seeing the sun exactly as it was, not as it is, for over 8 minutes after the event occurred. When you look up at the moon on a clear night, you're seeing it as it was approximately 1.3 seconds ago. Not much of a delay in practical terms, but still a delay nonetheless. When the Apollo astronauts walked on the moon's surface and communicated with mission control back on Earth, every single word they spoke took 1.3 seconds to reach Earth. And every response from mission control took another 1.3 seconds to travel back to the moon. This created a nearly 3-second gap in every single exchange of information. You can actually hear this delay clearly in the historical recordings of those conversations. There's always this noticeable pause, this awkward silence after someone speaks, before the response comes back. It's not because anyone is hesitating or thinking about their answer. It's simply the speed of light creating a fundamental limitation on how fast information can travel across space. When NASA sends commands to the Mars rovers, like Curiosity or Perseverance, the delay is much more significant and creates real operational challenges. Depending on where Mars is in its orbit relative to Earth, the signal can take anywhere from 3 minutes at the closest approach to 22 minutes when Mars is on the opposite side of the Sun from us. This means that if a rover is about to drive off a cliff or encounters some unexpected obstacle, there's absolutely no way to stop it in real time. By the time Mission Control sees the problem and sends a stop command, the rover would have already gone over the edge. This is why Mars rovers have to be semi-autonomous. They can't be driven like remote-control cars the way you might control a toy in your living room. The time delay is simply too great. The rovers need to be able to analyze their surroundings independently, make decisions about safe paths forward, and execute those decisions without constant human intervention. They're essentially driving themselves on an alien world millions of kilometers away, checking in with Earth only periodically to report what they've done and receive new general instructions for their mission. Calculating a light year. So, light travels 300,000 kilometers every single second. Now, let's work out together how far light can travel in an entire year, because that distance is what we call a light year. First, we need to figure out how many seconds are in a year. Let's break this down step by step so you can follow the calculation clearly. There are 60 seconds in every minute. That's simple enough, and something everyone knows from childhood. There are 60 minutes in every hour. Multiply those together, and you get 3,600 seconds in 1 hour. There are 24 hours in every day. Multiply that by 3,600 seconds per hour, and you get 86,400 seconds in a single day. Finally, there are approximately 365.25 days in a year. We say approximately because of leap years, which add an extra day every 4th year to keep our calendar synchronized with Earth's actual orbit around the Sunday. If we multiply 86,400 seconds per day by 365.25 days, we get approximately 31,557,600 seconds in one complete year. That's over 31 million seconds ticking by, one after another, from January 1st all the way through to December 31st, and then a bit more to account for those leap year adjustments. Now, remember, light travels 300,000 kilometers every single one of those seconds. It never stops, never slows down, never takes a break. It just keeps going at that same constant, relentless pace. If we multiply 300,000 kilometers by 31,557,600 seconds, we get approximately 9.46 trillion kilometers. Let me write that out more clearly for you, so you can truly see what we're dealing with. 9,460 billion kilometers. That is 1 light year. One single light year is approximately 9.46 trillion kilometers of distance through space. That's the distance light travels in 1 year of continuous motion at 300,000 kilometers per second. And this is why astronomers use light years instead of kilometers when discussing cosmic distances. It's so much easier to say Proxima Centauri is 4.24 light years away than to say Proxima Centauri is approximately 40 trillion kilometers away, or to write out the full number with all its zeros sprawling across the page. Putting a light year in perspective. Let's try to put this distance into some kind of perspective that might help you grasp its enormity, though I'll warn you right now that it's genuinely difficult. Remember earlier when we talked about the distance from Earth to the Sun being approximately 150 million kilometers? We established that this was an enormous distance that would take our fastest spacecraft months to traverse. Well, 1 light year is approximately 63,000 times that already enormous distance from Earth to the Sunday. If you could somehow stack the distance from Earth to the Sun 63,000 times, one on top of the other in a continuous line stretching out into space, you would have 1 light year. The Sun's distance, which already seemed incomprehensibly large when we discussed it earlier, becomes almost insignificantly tiny when compared to a light year. It's like comparing a single grain of sand to an entire beach stretching for kilometers in every direction. If you were traveling in a modern commercial airplane, cruising at a comfortable 900 kilometers per hour, how long would it take you to travel 1 light-year? Let's do the math together. 1 light-year is 9.46 trillion kilometers. Divide that by 900 kilometers per hour, and you get approximately 1.05 billion hours of continuous flight time. Convert that to years by dividing by the number of hours in a year, which is 8,760, and you get approximately 120,000 years. 120,000 years of continuous flight without stopping. Think about what that means for a moment. Modern humans, Homo sapiens, with brains essentially identical to ours, have only existed for approximately 200,000 years. Recorded human history only goes back about 5,000 years to the earliest writing systems. The entire span of human civilization, from the first agricultural settlements to the present day, is only about 12,000 years. You would need to fly continuously for 10 times the entire length of recorded human civilization just to travel one single light-year in a commercial airplane. But wait, it gets even more mind-bending when you really think about it. Remember, Proxima Centauri, our nearest stellar neighbor besides our own sun, is 4.24 light-years away from us. If you wanted to fly there in a commercial airplane traveling at 900 kilometers per hour, it would take you approximately 500,000 years of continuous flight. That's more than twice the entire time that modern humans have existed on Earth. You could start flying the moment the first modern humans appeared in Africa, continue flying through the entire development of human civilization, through all of recorded history, into the present day, and you'd still only be about halfway there. The fastest spacecraft we've ever built. Let's consider the fastest spacecraft humanity has ever built and launched into the cosmos. The Voyager 1 spacecraft, launched way back in September of 1977, is currently the most distant human-made object from Earth. It's been traveling through space for over 47 years now as of the time we're discussing this. It's currently moving at approximately 17 kilometers per second relative to the Sun, or roughly 61,200 kilometers per hour. That's incredibly fast by any human standard. It's 68 times faster than a commercial airplane. It would cross the entire United States from coast to coast in approximately 2.5 minutes. And yet, despite this incredible velocity maintained for nearly 5 decades, Voyager 1 has only traveled approximately 0.25% of the distance to Proxima Centauri. After nearly 50 years of traveling at over 60,000 kilometers per hour through space, through all of that time and distance, it's covered only 0.25% of the journey to the nearest star. At its current speed, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri if it were actually headed in that direction, which it isn't. But if it were, think about that time span. 73,000 years. The last ice age ended only about 11,700 years ago. Humans invented agriculture only about 12,000 years ago. The pyramids of Egypt were built approximately 4,500 years ago. The entire span of recorded human history, all the civilizations that have risen and fallen, all the wars fought and peace treaties signed, all the art created and destroyed, encompasses only about 5,000 years. Voyager 1 would need to travel for 15 times the entire length of recorded human history just to reach our nearest neighboring star. By the time it arrived, if somehow it could send a signal back to Earth, humanity would be unrecognizably different. Languages would have evolved and disappeared hundreds of times over. Entire civilizations would have risen, flourished, and crumbled to dust. The geography of Earth would have changed dramatically. It's genuinely hard to even imagine what humanity might be like 73,000 years from now, or if we'd even still exist as a species. The Parker Solar Probe, which I mentioned earlier, is even faster than Voyager 1. It reaches speeds of up to 192 kilometers per second, or approximately 691,200 kilometers per hour, when it's at its closest approach to the Sunday. This makes it the fastest human-made object ever created. Nothing we've ever built moves faster than this spacecraft. At this absolutely incredible velocity, it would still take approximately 6,700 years to reach Proxima Centauri. 6,700 years. That's longer than all of recorded human history. That's longer than humans have been writing, building cities, creating civilizations. The enormous implications. Do you see what I'm getting at here? Do you understand the enormity of what we're discussing? These aren't just big numbers that astronomers throw around to sound impressive. These are real distances that have genuine, profound implications for humanity's place in the universe and our ability to explore beyond our own solar system. Space is incomprehensibly vast. The distances between stars are so monumentally enormous that they genuinely challenge our ability to comprehend them with our evolved human brains. Even at speeds that seem impossibly fast by any human standard, even traveling faster than anything we've ever built in all of human history, the journey to even our nearest stellar neighbor would take thousands of years. Generations would be born, live their entire lives, and die aboard a spacecraft without ever reaching the destination. Their children would continue the journey, their grandchildren would continue. Their great-great-great-grandchildren, hundreds of generations removed from the original crew, would still be traveling through empty space with the destination still years or decades ahead. And remember, we're talking about just reaching our nearest neighbor, just the very first star beyond our own. Proxima Centauri is literally the closest we could possibly go, and it's still hopelessly, impossibly far away by any conventional means of travel. There are billions of other stars in our galaxy alone, most of them vastly farther away than Proxima Centauri. The Milky Way galaxy, our home galaxy that contains our sun and all the stars you can see with your naked eye on a clear night, is approximately 100,000 light-years across from edge to edge. 100,000 light-years. If you started at one edge of our galaxy and somehow traveled at the speed of light itself, not just close to it, but actually at light speed, the universal speed limit, it would take you 100,000 years to reach the other edge. The entire span of modern human existence would barely be enough time to cross our own home galaxy, even at the maximum possible speed that physics allows. The Milky Way and beyond. Our Sun, along with its family of planets, including Earth, is located approximately 26,000 light-years from the center of the Milky Way galaxy. We're out in one of the spiral arms, in a relatively quiet, stable region that astronomers sometimes call the galactic suburbs. The galaxy is rotating, spinning slowly through space, and our Sun takes approximately 230 million years to complete one full orbit around the galactic center. This period is sometimes called a galactic year or cosmic year. Think about that for a moment. The last time our Sun was in this same position in its orbit around the galaxy, dinosaurs were just beginning to appear on Earth. The first dinosaurs emerged during the Triassic period, approximately 230 million years ago. Since that time, dinosaurs evolved, flourished, dominated the planet for over 160 million years, and then went extinct 66 million years ago. Mammals evolved and spread across the planet. Primates appeared. Human ancestors diverged from other apes. Modern humans evolved. All of human history, everything that's ever happened on Earth involving our species, has occurred in just a tiny, insignificant sliver of one galactic orbit. The center of our galaxy is incredibly far away. 26,000 light-years means that when you look toward the galactic center on a clear night, you're seeing it as it was 26,000 years ago. You're looking back in time across an enormous gulf of space. The light that's hitting your eyes right now left the galactic center 26,000 years ago, when humans were still living in small hunter-gatherer tribes, when we hadn't yet invented agriculture, when we were just beginning to create the first cave paintings. If some enormous cosmic event occurred at the center of our galaxy right now at this very moment, if a massive supernova exploded or a black hole suddenly consumed a nearby star in a brilliant flash of radiation, we wouldn't know about it for 26,000 years. The event would happen, but the light carrying information about that event would take 26,000 years to reach us. Our descendants, thousands of generations from now, living in a world we couldn't possibly imagine, would be the ones to observe that event, not us. The nearest large galaxy to our own Milky Way is called Andromeda. You can actually see it with your naked eye on a very clear, dark night if you're far away from city lights. It appears as a faint, fuzzy patch of light in the constellation Andromeda. But that faint little patch is actually a massive galaxy containing approximately 1 trillion stars, roughly twice as many stars as our own Milky Way. It's approximately 2.5 million light-years away from us. 2.5 million light-years. When you look at the Andromeda galaxy through a telescope or see it in photographs, you're seeing it as it was 2.5 million years ago. You're literally looking back in time across an incomprehensible distance to see ancient light that began its journey toward Earth before modern humans even existed. 2.5 million years ago, our ancestors weren't even clearly distinguishable from other primates yet. Homo habilis, one of our early ancestors, was just beginning to use simple stone tools. If you somehow had a powerful enough telescope to see individual people on a planet orbiting a star in the Andromeda galaxy, and you looked through that telescope right now, you wouldn't see modern aliens living in the present moment. You'd see ancient aliens living 2.5 million years ago, doing whatever they were doing at that point in their civilization's history. If they're looking back at us with an equally powerful telescope, they're not seeing us. They're seeing Earth as it was 2.5 million years ago, seeing our ancestors making simple tools and beginning their long evolutionary journey toward humanity. The observable universe. The observable universe, which is the part of the universe we can theoretically see or detect with our instruments, is approximately 93 billion light-years across. Let me repeat that because it's genuinely difficult to comprehend. 93 billion light-years across. The entire observable universe, everything we can possibly see or detect, no matter how powerful our telescopes become, spans approximately 93 billion light-years from edge to edge. Now, you might be wondering, if the universe is only about 13.8 billion years old, according to our best current measurements, how can the observable universe be 93 billion light-years across? Shouldn't light have only had 13.8 billion years to travel, meaning the observable universe should only be about 27.6 billion light-years across at most? That's a really good question and shows you're thinking carefully about this. The answer involves something called cosmic expansion. The universe itself is expanding. Space itself is stretching and growing. Galaxies aren't just moving through space away from each other like cars on a highway. Space itself, the very fabric of reality that contains those galaxies, is expanding and carrying the galaxies along with it. This expansion means that objects that emitted light 13.8 billion years ago have since moved much farther away due to the expansion of space itself during the time their light has been traveling toward us. The most distant objects we can observe, the most ancient galaxies we can detect with our most powerful telescopes, are now approximately 46.5 billion light-years away from us due to this cosmic expansion, even though their light has only been traveling for 13.8 billion years. And because we can see in all directions, the total diameter of the observable universe is approximately 93 billion light-years. But here's something even more mind-bending to consider. The observable universe is almost certainly not the entire universe. It's just the part we can see, the part from which light has had time to reach us during the 13.8 billion years since the Big Bang. Beyond the edge of the observable universe, there's almost certainly more universe stretching out in all directions, potentially infinitely more. We can't see it, and we never will be able to see it, because the light from those regions hasn't had time to reach us yet, and due to cosmic expansion, it may never reach us. There could be countless billions or trillions of additional galaxies beyond the edge of what we can observe, entire regions of space completely and forever beyond our ability to detect or explore. The universe could be infinite in extent, stretching on forever in all directions, containing an infinite number of galaxies, stars, and planets. We simply don't know, and we may never be able to know for certain. Our view is limited by the finite speed of light, and the finite age of the universe. The speed of light has a universal limit. Now, you might be thinking, okay, space is big, distances are enormous. I get it, but why can't we just build a faster spacecraft? Why can't we just keep engineering better and better engines until we can travel at the speed of light or even faster? This is a natural question. Throughout human history, we've consistently broken through speed barriers. For centuries, people thought that traveling faster than a horse was impossible. Then we invented trains. People thought breaking the sound barrier was impossible. Then we built supersonic aircraft. So why should the speed of light be any different? Why can't we just keep pushing, keep innovating, until we find a way to go faster? The answer lies in the fundamental nature of reality itself, in the very fabric of space and time. According to Einstein's theory of relativity, which has been tested and confirmed thousands of times through countless experiments over more than a century, nothing that has mass can ever reach the speed of light, let alone exceed it. This isn't a technological limitation that we might overcome with better engineering. It's not like breaking the sound barrier or building a more powerful rocket engine. It's a fundamental law of physics that appears to be woven into the structure of the universe itself. Here's why. As an object with mass accelerates closer and closer to the speed of light, something very strange happens. The object's mass effectively increases from the perspective of an outside observer. The faster it goes, the more massive it becomes. This means that it requires more and more energy to continue accelerating it. As you approach the speed of light, your effective mass approaches infinity. To actually reach the speed of light would require infinite energy, which is obviously impossible. There's literally not enough energy in the entire universe to accelerate even a single atom to exactly the speed of light. You could harness the energy of every star, every galaxy, every bit of matter and energy in the entire cosmos, and it still wouldn't be enough. The speed of light isn't just a speed limit in the way that highway speed limits are arbitrary rules we've made up. It's a fundamental property of the universe, as unchangeable as the fact that 2 + 2 = 4. Light itself can travel at light speed, but only because photons, the particles that make up light, have no mass whatsoever. They're pure energy, and they always travel at exactly the speed of light, never faster, never slower. From the moment they're created to the moment they're absorbed by something, photons move at exactly 300,000 kilometers per second through empty space. They can't speed up or slow down. It's simply what they do by their very nature. Time dilation and relativity. But Einstein's relativity gives us something even stranger to think about, something that seems to contradict common sense but has been proven true through countless experiments. Time itself is not absolute. Time doesn't flow at the same rate for everyone, everywhere in the universe. Time is relative. It depends on how fast you're moving and how strong the gravitational field is around you. If you were somehow traveling in a spacecraft, moving at a significant fraction of the speed of light, time would actually slow down for you relative to people back on Earth. This isn't science fiction. It's not a theory or a hypothesis. It's established scientific fact that's been proven over and over again through experiments. From your perspective, inside the spacecraft, everything would feel completely normal. Your heart would beat normally. Your thoughts would proceed normally. Time would feel like it was passing at exactly the same rate it always has throughout your entire life. But if you could somehow compare your clock to a clock back on Earth, you'd discover something shocking. Less time has passed for you than has passed for the people you left behind. This effect is called time dilation, and it becomes more and more pronounced the closer you get to the speed of light. At lower speeds, the effect is tiny, almost negligible. But as you approach light speed, it becomes enormous and impossible to ignore. Let me give you a concrete example to help illustrate this mind-bending concept. Imagine you board a spacecraft capable of traveling at 99.5% of the speed of light. You leave Earth and travel to a star that's 100 light-years away. From Earth's perspective, watching you go, your journey would take approximately 100 years to reach the star at that speed. But from your perspective, inside the spacecraft, due to time dilation, the journey would only feel like it took about 10 years. You'd experience 10 years passing. You'd age 10 years. Your body would change in all the ways it would normally change over a decade. But when you arrived at your destination and looked back at Earth, 100 years would have passed there. Everyone you knew would be dead. Your children would be elderly or deceased. Your grandchildren might be elderly. The world would have changed beyond recognition. Buildings you remembered would be gone. Technology would be unrecognizably advanced. History would have marched forward for a full century, while you experienced only a decade. If you turned around and came back to Earth at the same speed, another 100 years would pass on Earth from their perspective, while only another 10 years would pass for you. You'd return to Earth having aged only 20 years total, but 200 years would have passed on Earth. You'd be returning to a world 2 centuries in the future from when you left. Everyone you ever knew would be long dead. Entire generations would have been born, lived, and died while you were gone. This isn't theoretical speculation. Time dilation is real, and we've measured it directly. Atomic clocks, which are incredibly precise timepieces that can measure time down to billionths of a second, have been put on aircraft and flown around the world at high speeds. When compared to identical atomic clocks that stayed on the ground, the traveling clocks showed slightly less time had passed, exactly as Einstein's equations predicted. The effect was tiny because the aircraft were traveling so much slower than light speed, but it was measurable and precisely matched the theoretical predictions. Satellites in orbit around Earth, including the GPS satellites that help your phone tell you where you are, experience time slightly differently than we do on Earth's surface because they're moving faster than us and are in a slightly weaker gravitational field. If we didn't account for this time dilation effect in the GPS system's programming, the navigation system would quickly become inaccurate. The errors would accumulate rapidly, and within just a few hours, your GPS would be telling you you're in the wrong location by several kilometers. The fact that GPS works correctly is actually a constant, everyday proof that relativity is real and that time dilation actually happens. Practical implications for space travel. So, even if we somehow develop the technology to build spacecraft capable of traveling at a significant fraction of light speed, which would require solving enormous engineering challenges and harnessing unimaginable amounts of energy, space travel to distant stars would still present almost insurmountable problems due to these relativistic effects and the vast distances involved. Let's imagine humanity develops fusion engines or antimatter drives or some other advanced propulsion technology that can accelerate a spacecraft to half the speed of light. That's enormously optimistic and probably centuries beyond our current capabilities. But let's imagine it for the sake of argument. At half-light speed, traveling to Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away, would take approximately 8.5 years from Earth's perspective. That sounds almost manageable, doesn't it? Not exactly a quick trip, but within a human lifetime, astronauts could potentially make the journey. But there are enormous complications. First, accelerating to half the speed of light would require absolutely staggering amounts of energy. We're talking about energy levels far beyond anything we can currently produce. The fuel requirements alone would be extraordinary. You'd need to carry enough fuel not just to accelerate to half light speed, but also to decelerate when you reach your destination. Otherwise, you'd just fly right past at incredible speed with no way to stop. Second, at half the speed of light, even tiny particles of dust floating in interstellar space become deadly projectiles. A single grain of sand hitting your spacecraft at half-light speed would impact with the energy of a large bomb. The kinetic energy involved is just enormous. You'd need incredibly strong shielding to protect the spacecraft and its crew from these high-speed collisions with interstellar matter. The engineering challenges are almost beyond comprehension with current technology. Third, there's the problem of communication. Once you're light years away from Earth, communication becomes extremely slow. A message sent from Proxima Centauri takes 4.24 years to reach Earth. A response takes another 4.24 years to get back to you. That's a nearly 9-year gap between sending a message and receiving a reply. You can't have a conversation. You can't ask for help if something goes wrong. You can't receive updated instructions based on new discoveries. You're truly on your own, more isolated than any humans have ever been in history. And remember, this entire scenario assumes we've solved the enormous technological challenges of accelerating a spacecraft to half the speed of light in the first place, which we're currently nowhere close to being able to do. The fastest spacecraft we've actually built, remember, travels at less than 0.1% of light speed. We're not just a little bit away from half light speed. We're several orders of magnitude away from it. It's the difference between walking speed and supersonic flight. The technological gulf is vast, traveling to distant stars. For more distant stars, the problems become even more extreme. Betelgeuse is a red supergiant star that you can see in the constellation Orion. It's one of the brightest stars in the night sky and very distinctive because of its reddish color. Betelgeuse is approximately 550 light-years away from Earth. Even traveling at half the speed of light, which again is wildly optimistic with current or near-future technology, the journey would take 1,100 years. 1,100 years. To put that in perspective, 1,100 years ago, it was the year 926. The Vikings were still raiding coastal settlements across Europe. The medieval period was in full swing. Modern nations like the United States, Canada, and Australia didn't exist and wouldn't exist for centuries. The scientific method hadn't been invented yet. People still thought the Earth was the center of the universe with everything revolving around it. The entire worldview of humanity was completely different from today. No single human could make such a journey. It would require a generation ship, a massive spacecraft designed to support a self-sustaining population over many generations. People would be born on the ship, live their entire lives traveling through the darkness of interstellar space, and die aboard the ship, never setting foot on either Earth or the destination planet. Their children would do the same, and their grandchildren. Dozens of generations would pass during the journey. The people who eventually arrived at Betelgeuse would be the distant descendants of the original crew, separated from them by perhaps 40 or 50 generations of births and deaths. Would they even still speak the same language as the original crew? Would they remember Earth? Or would it have become a distant myth to them? Would they still be committed to the original mission after generations of living in space? Or would they have developed their own culture and goals? These aren't just engineering questions. They're profound social, psychological, and philosophical questions about human nature and society. And that's just to reach a star that's relatively close by in galactic terms. There are stars on the other side of our galaxy that are 100,000 light-years away. Even at light speed itself, the maximum possible velocity that physics allows, it would take 100,000 years to reach them. At more realistic speeds, like half light speed or 10% light speed, it would take hundreds of thousands or even millions of years. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. Even at light speed, reaching it would take 2.5 million years. At realistic spacecraft speeds, it would take tens of millions of years. The scale of the universe. These timescales are so enormous that they become almost meaningless to human comprehension. Our brains didn't evolve to think in terms of millions of years. We evolved to think in terms of seasons, years, maybe decades if we're planning long-term. Even thinking in terms of centuries is difficult for us. But millions of years? That's beyond human timescales entirely. It's geological time, evolutionary time, the time it takes for entire species to evolve and go extinct. This is the reality of the universe we live in. Space is incomprehensibly vast. Distances between stars are enormous, beyond human comprehension. The speed of light, despite being incredibly fast, is still painfully slow, when measured against cosmic distances. Even traveling at light speed, which is impossible for anything with mass according to our current understanding of physics, the universe would still be mind-bogglingly huge and largely unreachable. The observable universe contains an estimated 200 billion to 2 trillion galaxies. Let me repeat that. Between 200 billion and 2 trillion galaxies. Each of those galaxies contains anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated to be somewhere around 1 septillion. That's a 1 followed by 24 zeros. Written out fully, it's 1 million trillion stars. The total number of planets is presumably even larger, since many stars have multiple planets orbiting them. With numbers like these, the probability seems overwhelming that life must exist somewhere else in the universe besides Earth. The sheer number of possible locations is staggering. Even if the probability of life arising on any given planet is extremely small, with 1 septillion stars and potentially trillions of planets, the odds seem to favor life arising in at least some places. Perhaps in many places, perhaps in countless places, scattered throughout the cosmos. And yet, despite the enormous numbers, despite the seemingly favorable odds, we've never detected any sign of extraterrestrial life. We've never received any radio signals that are clearly artificial. We've never observed any structures or activities in space that are obviously the work of technological civilizations. We've never been visited by aliens, despite what various conspiracy theories might claim. We appear to be utterly alone in an enormously vast universe teeming with trillions of planets. The Fermi paradox. This apparent contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If the universe is so vast and contains so many potential homes for life, and if life is even reasonably common, then why haven't we seen any evidence of it? Where are all the alien civilizations? Why haven't they contacted us? Why haven't we detected their radio signals or observed their megastructures or noticed their spacecraft?" There are many proposed answers to this paradox, and none of them are particularly comforting. One possibility is that life is actually extraordinarily rare, much rarer than our naive calculations might suggest. Perhaps the combination of conditions necessary for life to arise and evolve is so specific, so unlikely, that it's only happened once or a handful of times in the entire observable universe. Perhaps Earth is truly special, a rare oasis of biology in a vast cosmic desert. This would make us incredibly precious, but also incredibly lonely. Another possibility is that life is common, but intelligent life is rare. Perhaps single-celled organisms are scattered across billions of planets throughout the universe, but the evolutionary path from simple cells to complex multicellular organisms to intelligence is so difficult, so unlikely, that it almost never happens. Earth has been inhabited by life for approximately 3.5 billion years, but intelligent, technological civilization only arose in the last few thousand years. For over 99.9% of life's history on Earth, there was no intelligence, no technology, no civilization capable of sending signals into space. Perhaps most planets with life never progress beyond the equivalent of our bacteria or our dinosaurs. A third, darker possibility is that intelligent civilizations do arise regularly throughout the universe, but they inevitably destroy themselves before they can spread to the stars. Perhaps technological civilizations naturally develop weapons or technologies that lead to their own extinction. Nuclear weapons, artificial intelligence, bioengineered diseases, environmental collapse, any of these could potentially wipe out a civilization that develops them. Perhaps the universe is littered with the ruins of dead civilizations that destroyed themselves shortly after achieving technology. Perhaps we're currently in that dangerous window ourselves, where we have the technology to destroy ourselves but haven't yet developed the wisdom and social structures to prevent it. A fourth possibility, perhaps the most relevant to our current discussion, is the sheer tyranny of distance. Perhaps there are thousands or millions of intelligent civilizations scattered throughout the galaxy. but they're all so enormously far apart that communication or travel between them is effectively impossible. Remember, even our nearest stellar neighbor is over 4 light years away. Any message sent to them would take over 4 years to arrive, and another 4 years for a response. That's an 8-year minimum for a simple back-and-forth exchange of information. For more distant civilizations, the delays become prohibitive. A civilization 1,000 light-years away would have a 2,000-year communication delay. If they sent us a message today, it would arrive in the year 3026. Our response would reach them in the year 5026. That's not a conversation. That's barely even communication in any meaningful sense. It's more like sending messages in bottles into an ocean and hoping someone eventually finds them, knowing that you'll be long dead before any reply could possibly reach you. And travel is even more difficult than communication. As we've discussed extensively, even with incredibly advanced technology that we can barely imagine, interstellar travel would take decades, centuries, or millennia depending on the distance and the speed achieved. Perhaps civilizations simply can't spread far beyond their home star systems because the distances are too vast, the journey too long, the energy requirements too extreme. Perhaps the universe is filled with isolated pockets of civilization, each one developing independently, unaware of the others, separated by light years of empty space that they simply cannot cross in any practical way. Looking up at the night sky. When you look up at the night sky on a clear night, far from city lights, you can see approximately 3,000 stars with your naked eye. Every single one of those stars is part of our Milky Way galaxy. The most distant individual stars you can see with your naked eye are approximately 15,000 light-years away. That might sound like an enormous distance, and it absolutely is. But remember that our galaxy is 100,000 light-years across. You're only seeing stars in our immediate cosmic neighborhood, a tiny bubble of space around Earth. The vast majority of stars in our own galaxy are completely invisible to your naked eye, far too distant and dim for you to perceive without a telescope. And yet, even though you're only seeing the tiniest fraction of the stars in our galaxy, only the ones closest to us, the view is still spectacular and humbling. Every single point of light you see in the night sky is a sun, often much larger than our own. Many of those stars have their own planets orbiting them. Some of those planets might be similar to Earth in size and temperature. Some might even harbor life, though we have no way of knowing for certain without visiting them or studying them much more closely than our current technology allows. When you look at a star in the night sky, you're not seeing it as it is right now in the present moment. You're seeing it as it was when the light you're observing left that star's surface and began its long journey through space toward Earth. Most of the stars you can see with your naked eye are dozens or hundreds of light-years away. You're literally looking back in time, seeing ancient light from the past. Sirius, the brightest star in the night sky besides our own sun, is approximately 8.6 light-years away. When you look at Sirius tonight, you're seeing it as it was 8.6 years ago. You're seeing light that left Sirius's surface in late 2017 or early 2018, traveled through the void of space for over 8 years, and is only now reaching your eyes. If something dramatic happened to Sirius today, if it suddenly dimmed or exploded or changed in some fundamental way, you wouldn't know about it until 2034. Vega, another bright star that's very prominent in summer skies in the northern hemisphere, is approximately 25 light-years away. The light you see when you look at Vega tonight left that star's surface in the year 2001, around the time of the September 11th attacks, the early days of the War on Terror, when flip phones were still the dominant mobile technology and social media didn't exist yet. That light has been traveling through empty space for a quarter century to reach your eyes tonight. Betelgeuse, which we mentioned earlier, that distinctive red star in Orion's shoulder, is approximately 550 light-years away. When you look at Betelgeuse, you're seeing it as it was in the late 1400s, during the European Renaissance. Christopher Columbus was still alive. Leonardo da Vinci was painting the Mona Lisa. The printing press had just been invented. The Protestant Reformation hadn't happened yet. The light you're seeing left Betelgeuse's surface during that historical period and has been traveling ever since, crossing the vast emptiness of interstellar space for over 5 centuries. Betelgeuse is actually a fascinating case because it's a dying star. It's a red supergiant in the final stages of its life. Astronomers know that sometime in the relatively near future, in cosmic terms, Betelgeuse will explode in a supernova. When it does, it will be one of the most spectacular astronomical events visible from Earth in human history. It will be bright enough to see during the daytime for weeks or months. It will be clearly visible even in light-polluted cities. It will be the most dramatic change in the appearance of the night sky that any human has witnessed in recorded history. But here's the thing. Betelgeuse might have already exploded. The explosion might have already happened. Betelgeuse could have gone supernova in the year 1500, or 1600, or 1700, or any time up until 550 years ago. If it exploded 500 years ago, the light from that explosion is traveling toward us right now at this very moment. But it won't reach Earth for another 50 years. We won't see it until 2076. If it exploded 200 years ago, we won't see it until 2376. We have absolutely no way of knowing what's happening at Betelgeuse right now. We can only see its distant past. This is the strange reality of living in a universe where light speed, though incredibly fast, is still finite. We can never see the present moment anywhere except right here where we are. Everything else we observe is necessarily in the past. The farther away something is, the deeper into the past we're looking. Astronomy isn't just the study of space, it's also the study of time, of history, of events that happened long ago in distant places across the cosmos. The cosmic microwave background. The most distant thing we can observe in the entire universe is called the cosmic microwave background radiation. This is light that was emitted approximately 13.8 billion years ago, shortly after the Big Bang itself. At that time, the universe was much smaller, hotter, and denser than it is today. It was filled with a hot, glowing plasma of particles. As the universe expanded and cooled, that plasma eventually became transparent, and the light that was trapped in it was released to travel freely through space. That ancient light has been traveling through the expanding universe for 13.8 billion years. It's been stretched and redshifted by cosmic expansion, transforming from visible light into microwave radiation. That's why we call it the cosmic microwave background. It's not visible to our eyes anymore because the wavelength has been stretched too long by the expansion of space over billions of years. But we can detect it with specialized instruments, and we can map it across the entire sky. When astronomers observe the cosmic microwave background, they're literally looking at the edge of the observable universe, seeing light from the earliest moments of cosmic history. They're observing events that happened 13.8 billion years ago, when the universe was only about 380,000 years old. That's infancy in cosmic terms. The universe today is approximately 45,000 times older than it was when that light was emitted. We can't see any farther back than the cosmic microwave background because before that point, the universe was opaque. Light couldn't travel freely. It was constantly being absorbed and re-emitted by the dense plasma that filled all of space. There's no light from earlier times for us to observe. The cosmic microwave background is effectively a wall in time beyond which we cannot see, no matter how powerful our telescopes become. This ancient light surrounds us on all sides, coming from every direction in space. Wherever you look in the sky, if you could see in microwave wavelengths, you'd see this faint glow from the early universe. It's incredibly uniform in temperature and intensity, varying by only about 1 part in 100,000 across the sky. These tiny variations, these slight differences in temperature from one region to another, are actually crucial. They represent tiny density fluctuations in the early universe that eventually, over billions of years, grew into the galaxies, galaxy clusters, and large-scale structures we see today. The cosmic microwave background is perhaps the most important piece of evidence we have for the Big Bang theory. It's exactly what the theory predicts we should see, and its properties match the theoretical predictions with remarkable precision. It's a snapshot of the universe in its infancy, preserved in light that's been traveling for nearly the entire age of the cosmos. Our place in space and time. Think about what all of this means for our place in the universe. We live on a small planet orbiting an ordinary star in the outer regions of an ordinary galaxy. There's nothing particularly special or unique about our location from a cosmic perspective. Our sun is one of hundreds of billions of stars in the Milky Way. The Milky Way is one of hundreds of billions or trillions of galaxies in the observable universe. Earth is one of trillions of planets scattered throughout the cosmos. We're not at the center of anything. We're not in any kind of privileged position. We're just here, on this particular planet, orbiting this particular star, in this particular galaxy, in this particular region of the universe. From a cosmic perspective, we're insignificant, tiny beyond measure, living our brief lives on a speck of dust floating in an incomprehensibly vast cosmos. And yet, despite this cosmic insignificance, we're also remarkable. As far as we know, we're the only place in the entire observable universe where life has arisen and evolved to the point of developing intelligence, consciousness, and technology. We're the only beings we know of that can look up at the cosmos and try to understand it. We're the universe become aware of itself, matter arranged in such a way that it can ponder its own existence. We've only been doing science in any systematic way for about 400 years, since the scientific revolution of the 1600s. In that relatively brief time, we've figured out an enormous amount about how the universe works. We've discovered that the Earth orbits the Sun, not the other way around. We've discovered that stars are distant suns, not holes in a celestial sphere. We've discovered that galaxies exist beyond our own, billions of them scattered throughout space. We've measured the age of the universe. We've detected gravitational waves, ripples in the fabric of space-time itself. We've found thousands of planets orbiting other stars. We've gone from thinking the Earth was the center of everything to understanding that we're on a planet orbiting an ordinary star in an ordinary galaxy in a vast universe containing billions of galaxies. That's a dramatic shift in perspective, accomplished in just a few centuries of scientific investigation. And we've done all of this while confined to our own planet and its immediate vicinity. No human has traveled farther than the moon. All of our direct exploration has been limited to this tiny bubble of space immediately around Earth. Everything else we know about the cosmos has been learned by observing light. Light from the sun, from the moon, from planets, from stars, from galaxies, from the cosmic microwave background. Light is our window into the universe. It's the messenger that brings us information from distant places and distant times. And that messenger travels at exactly 300,000 kilometers per second. No faster, no slower. The speed of light is the speed at which information propagates through the universe. The isolation of civilizations. This fundamental speed limit has profound implications for the possibility of intelligent life elsewhere in the universe and our ability to ever interact with such life, if it exists. Even if the universe is teeming with intelligent civilizations, even if they're relatively common on a cosmic scale, they're likely spread out across enormous distances. The nearest one might be dozens or hundreds or thousands of light years away from us. If there's an intelligent civilization 100 light years away, and they're looking at Earth right now with powerful telescopes, they're not seeing us. They're seeing Earth as it was in 1926. They're seeing a world before computers, before nuclear weapons, before space travel, before television. If they tried to send us a message today, we wouldn't receive it until 2126, over a century from now. If we sent them a message today, they wouldn't receive it until 2126, and we wouldn't get their reply until 2226, 200 years from now. The delay makes real-time communication or interaction completely impossible. Any relationship between civilizations separated by light years of distance would be conducted over timescales of centuries or millennia. It wouldn't be a dialogue. It would be more like an exchange of letters where each letter takes centuries to arrive. By the time a response comes back, the civilization that sent the original message might have changed beyond recognition, or might not even exist anymore. Civilizations rise and fall. Empires emerge and collapse. Technologies advance and become obsolete. Languages evolve and change. Entire cultures transform over the course of centuries. The Romans built one of the greatest empires in human history, and it lasted approximately 1,000 years before it fell. The Byzantine Empire lasted another 1,000 years after that before finally collapsing. That's 2,000 years total, and yet even that enormous span of time would only allow for 10 back-and-forth exchanges with a civilization 100 light-years away. Most civilizations don't last that long. Most civilizations are transient things, lasting a few centuries or maybe a millennium before being conquered, absorbed, or transforming into something else. Modern nation-states are typically only a few hundred years old at most. The United States has existed for less than 250 years. China, as a continuous civilization, is unusual in having maintained cultural continuity for thousands of years. But even China has gone through numerous dynasties, governments, and transformations during that time. If human civilization sends a message to a star system 100 light-years away and receives a response 200 years later, will the civilization that receives the response still remember sending the original message? Will they still care about the answer? Will they even still be using the same technology to detect the response? Will they still speak the same language? These are genuine questions with uncertain answers. The loneliness of intelligence. The universe might be filled with intelligent civilizations, but if they're all separated by dozens or hundreds or thousands of light years, they might as well be alone for most practical purposes. They can't visit each other, they can't have conversations, they can't trade or share technology in any real-time way. They can only send messages into the void and hope that someone receives them generations or centuries later. This creates a sort of cosmic loneliness. Even if we're not alone in the universe, even if there are billions of other intelligent species scattered among the stars, we're still effectively isolated from them by the tyranny of distance and the finite speed of light. We're like islands in an enormous ocean, able to see other islands in the extreme distance, but unable to reach them or communicate with them in any meaningful way. Some scientists have proposed ways around this limitation. Theoretical concepts like wormholes, which would be shortcuts through space-time connecting distant regions of space, or warp drives, which would somehow bend space around a spacecraft to allow faster-than-light travel. These concepts don't necessarily violate relativity because they don't involve traveling through space faster than light, but rather manipulating space itself. However, all of these concepts remain purely theoretical. We have no idea if they're actually possible. And if they are possible, whether they require exotic forms of matter or energy that might not even exist in our universe. We certainly don't have the technology to create them, and we may never develop such technology. It's possible that the laws of physics simply don't allow for any shortcuts or loopholes around the speed of light limitation. It's possible that the universe really is structured in such a way that different civilizations are permanently isolated from each other by distance. The observable universe as a horizon. There's another limitation imposed by the finite speed of light, combined with cosmic expansion. As we discussed earlier, the observable universe is approximately 93 billion light-years across. But observable is the key word there. That's the part of the universe from which light has had time to reach us. Beyond that boundary, there are regions of space from which light has not yet had time to reach us. But it's actually more complicated than that because of cosmic expansion. The universe isn't just big and static. It's actively expanding, and the farther away something is, the faster it's receding from us due to the expansion of space itself. At great enough distances, space is expanding faster than the speed of light. This doesn't violate relativity because the space itself is expanding. not objects moving through space, but it has the same practical effect. There's a distance called the cosmic event horizon, beyond which objects are receding from us faster than light due to cosmic expansion. Light from those objects will never reach us, no matter how long we wait, because the space between us and them is expanding faster than the light can cross it. The light is still traveling toward us at 300,000 kilometers per second, but the space it's traveling through is expanding faster than that, so it never makes any progress toward us. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. This means there are galaxies, potentially billions or trillions of them, that we will never be able to see, no matter how long we wait or how powerful our telescopes become. They're not just too far away. They're fundamentally and permanently beyond our cosmic horizon. And that horizon is actually shrinking over time as cosmic expansion accelerates. Galaxies that we can see today will eventually, billions of years in the future, recede beyond our cosmic horizon and disappear from view forever. The universe is becoming more isolated over time. In the far future, trillions of years from now, the universe will be a much lonelier place. Most galaxies will have receded beyond the cosmic horizon. An intelligent civilization arising in that far future would look out at the universe and see only their own galaxy and perhaps a few nearby companions. The billions of galaxies we can see today would be long gone, having disappeared beyond the cosmic horizon. That future civilization might conclude that their galaxy is the entire universe, because they'd have no way to observe anything beyond it. The ancient photons reaching Earth. Every photon of light that enters your eye has its own story, its own journey through space and time. When you look at the moon, the photons hitting your retina left the moon's surface 1.3 seconds ago. They reflected off the gray, dusty surface of our satellite, traveled through the vacuum of space, passed through Earth's atmosphere, and reached your eye. Those photons have been traveling for just over a second, covering 384,000 kilometers on their brief journey. When you look at the sun during sunrise or sunset, when it's safe to glance at it briefly, the photons you're seeing began their journey 8 minutes and 20 seconds ago. But actually, those photons have a much longer and more complex history than that. They were created deep in the core of the sun through nuclear fusion reactions. Hydrogen atoms fused together to create helium, releasing energy in the form of gamma-ray photons. But those gamma-ray photons couldn't simply fly straight out of the sunday. The sun is incredibly dense, packed with matter, and those photons constantly collided with atoms, being absorbed and re-emitted over and over again in a random walk toward the surface. A photon created in the sun's core takes approximately 100,000 to 1 million years to work its way to the surface through this process of constant absorption and re-emission. Only when it finally reaches the surface can it escape into space and travel freely. So when you look at the sun, you're seeing light that was created in fusion reactions hundreds of thousands or even millions of years ago. Light that finally escaped the sun's surface 8 minutes ago. You're looking at ancient energy, created long before humans existed, that has finally completed its journey and reached your eyes. The warmth you feel on your face when you stand in sunlight is energy that was created deep in the sun's core while mammoths still walked the earth. Energy that has been slowly working its way to the surface ever since. When you look at Proxima Centauri through a telescope, the photons entering the telescope began their journey 4.24 years ago. They left the surface of that distant star in late 2021 or early 2022 during the COVID-19 pandemic and have been traveling through empty space ever since. They've crossed 4.24 light-years of void, roughly 40 trillion kilometers of absolutely empty space, to finally reach Earth and enter your telescope. Each photon has been traveling alone through the darkness, moving at 300,000 kilometers per second, never slowing, never stopping, for over 4 years. The photons from more distant stars have even more epic journeys. Photons from stars 1,000 light-years away left their origin when medieval knights were fighting in the Crusades, when Genghis Khan was building his empire. when the Aztec civilization was just beginning to rise in Mesoamerica. Those photons have been traveling through space for a millennium, crossing a distance of about 9 quadrillion kilometers, to finally arrive at Earth and be detected by our telescopes tonight. Some of the photons we detect from very distant galaxies have been traveling for billions of years. They left their source galaxies when the universe was much younger, when our solar system didn't exist yet, when the Milky Way looked very different from how it appears today. Those photons have crossed billions of light years of expanding space, have been stretched and redshifted by cosmic expansion, and have finally, after an unimaginably long journey, been captured by our most powerful telescopes. Each of those ancient photons carries information about the distant past. By studying them, we can learn about conditions in the early universe, about how galaxies formed and evolved, about the chemical composition of distant stars, about the expansion rate of space itself. Light isn't just a pretty thing to look at, it's a messenger, carrying encoded information across vast distances and enormous spans of time. Every photon is a tiny time capsule, preserving information about the conditions at its source and the journey it took to reach us. The tools we use to measure distance. Given how vast these cosmic distances are, you might wonder how we actually measure them. How do we know that Proxima Centauri is 4.24 light-years away? How do we know that the Andromeda Galaxy is 2.5 million light-years away? We can't exactly take a tape measure and stretch it across space. We can't send a spacecraft to these places and time how long it takes because, as we've discussed, the travel times would be thousands or millions of years, even at impossible speeds. So how do we determine these enormous distances? For relatively nearby stars, within a few hundred light-years of Earth, astronomers use a technique called parallax. This is based on the same principle your brain uses to perceive depth with your two eyes. Hold your finger up in front of your face and look at it with just your left eye, then just your right eye, alternating back and forth. Notice how your finger appears to shift position relative to the background? That's parallax. Your two eyes see the finger from slightly different angles, and your brain uses that difference to calculate how far away your finger is. Astronomers do the same thing, but instead of using two eyes, they use Earth's orbit around the Sun as their baseline. They observe a star's position against the background of much more distant stars in winter, when Earth is on one side of the sunday. Then they observe the same star 6 months later in summer, when Earth is on the opposite side of the Sun, 300 million kilometers away from where it was. If the star is relatively close, it will appear to shift slightly against the background of more distant stars, just like your finger shifted when you looked at it with different eyes. By measuring this tiny shift and using some straightforward trigonometry, astronomers can calculate the distance to the star. The closer the star, the bigger the shift. The farther the star, the smaller the shift. For very distant stars, the shift becomes so tiny that it's incredibly difficult to measure accurately, even with our best instruments. The European Space Agency's Gaia satellite, launched in 2013, has measured parallaxes for approximately 1.3 billion stars, creating the most detailed three-dimensional map of our galactic neighborhood ever produced. But parallax only works for relatively nearby stars. Beyond a few thousand light-years, the shifts become so minuscule that even our most precise instruments can't measure them reliably. For more distant objects, astronomers need different methods. They use what are called standard candles, objects whose intrinsic brightness is known. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, and you can see how bright it looks from where you're standing, you can figure out approximately how far away it must be. A 100-watt bulb looks bright from across the room, but dim from across a football field. By measuring the apparent brightness, you can work backwards to determine the distance. One of the most important standard candles in astronomy is a type of star called a Cepheid variable. These are stars that pulse regularly, getting brighter and dimmer in a predictable cycle. The remarkable thing about Cepheid variables is that their intrinsic brightness is directly related to their pulsation period. A Cepheid that pulses once every 10 days is intrinsically brighter than one that pulses once every 5 days. This relationship was discovered by astronomer Henrietta Swan Leavitt in 1912, and it revolutionized our ability to measure cosmic distances. By observing a Cepheid variable and measuring its pulsation period, astronomers can determine its intrinsic brightness. Then, by measuring how bright it appears from Earth, they can calculate its distance. This method works for distances up to about 100 million light-years, far enough to reach many nearby galaxies. In fact, Cepheid variables were the key to determining that Andromeda was actually a separate galaxy beyond our own Milky Way, rather than a nebula within our galaxy as was previously believed. For even greater distances, astronomers use Type Ia supernovae, which are explosions of white dwarf stars that occur when the star reaches a critical mass. These explosions are remarkably consistent in their intrinsic brightness, making them excellent standard candles for measuring distances to very distant galaxies billions of light-years away. In fact, observations of distant Type Ia supernovae in the late 1990s provided the first strong evidence that the expansion of the universe is accelerating, a discovery that led to the 2011 Nobel Prize in Physics. The cosmic distance ladder. These various methods are often called the cosmic distance ladder because each method builds on the previous one, allowing us to reach farther and farther into space. We use parallax to measure distances to nearby stars. We use those measurements to calibrate Cepheid variables. We use Cepheid variables to calibrate Type Ia supernovae. Each rung of the ladder allows us to climb higher, to reach greater distances. It's an intricate, carefully constructed system, and it's a testament to human ingenuity that we've been able to measure distances across billions of light-years while confined to a single planet. We've never left our immediate cosmic neighborhood, and yet we've mapped the large-scale structure of the observable universe. We've determined its size, its age, its composition, and its fate, all by carefully observing light and developing clever methods to interpret what that light tells us. But it's important to understand that these distance measurements contain uncertainties. The farther away something is, the more uncertainty there is in our distance measurement. For nearby stars measured by parallax, we might know the distance to within 1% accuracy. For distant galaxies measured using Type Ia supernovae, the uncertainty might be 5 or 10%. These uncertainties compound as we go up the distance ladder, because each rung depends on the calibration from the previous rung. This is why you'll sometimes see slightly different numbers for the same distance, depending on the source. Different studies might use slightly different methods or assumptions, leading to slightly different results. But generally speaking, for well-studied objects, different methods agree with each other to within their uncertainties, which gives us confidence that we're measuring real distances and not just making things up. The fact that multiple independent methods give consistent results is powerful evidence that we actually understand what we're doing. The expansion of space and dark energy. One of the most profound discoveries about the universe in the past century is that space itself is expanding. This isn't a matter of galaxies moving through space away from each other, like cars driving away from each other on a highway. Space itself, the very fabric of the universe, is expanding and stretching, carrying galaxies along with it. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move away from each other, not because they're moving across the balloon's surface, but because the surface itself is expanding. That's analogous to what's happening with galaxies in our universe. Though it's important to note that the analogy is imperfect, because the universe isn't expanding into anything the way a balloon expands into the air around it. Edwin Hubble discovered cosmic expansion in 1929 by observing that distant galaxies appear to be moving away from us, and the farther away they are, the faster they appear to be receding. This relationship, now called Hubble's law, was revolutionary because it implied that the universe had a beginning. If you run the expansion backward in time, everything gets closer and closer together until, approximately 13.8 billion years ago, everything was compressed into an infinitely dense point. That moment is what we call the Big Bang. The expansion of the universe has been happening ever since the Big Bang, and it's still continuing today. But here's something even stranger. In 1998, two teams of astronomers made a shocking discovery. They were studying distant Type Ia supernovae, trying to measure the expansion rate of the universe and expecting to find that the expansion was gradually slowing down due to gravity pulling everything back together. Instead, they found the opposite. The expansion is speeding up. The universe isn't just expanding, it's expanding faster and faster over time. This acceleration requires some kind of energy that's pushing space apart, working against gravity. Astronomers call this mysterious energy dark energy, and we have absolutely no idea what it actually is. It's one of the biggest mysteries in modern physics. Dark energy appears to make up approximately 68% of all the energy in the universe. Dark matter, another mysterious substance that we can only detect through its gravitational effects, makes up approximately 27%. Normal matter, the atoms that make up stars, planets, and everything we can see and touch, makes up only about 5%. We live in a universe where 95% of its content is stuff we don't understand at all. We can detect its effects. We can measure how much of it there is, but we don't know what it's made of or why it exists. Dark energy has profound implications for the future of the universe. Because the expansion is accelerating, galaxies that are already very far away from us will continue to recede faster and faster. Eventually, billions of years in the future, most galaxies will be receding from us faster than light due to cosmic expansion, and they'll disappear beyond our cosmic event horizon forever. The universe will become an increasingly lonely place as more and more galaxies vanish from view, our cosmic neighborhood. Despite the vast scale of the universe and the enormous distances we've been discussing, it's worth taking a moment to appreciate our local cosmic neighborhood. The Sun and its family of planets exist within the Milky Way galaxy, which is our home on the grandest scale. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms winding outward from the ends of the bar. It's approximately 100,000 light-years in diameter and about 1,000 light-years thick in the disk, though the central bulge is thicker. The entire galaxy contains an estimated 200 to 400 billion stars, though the exact number is uncertain because many stars are hidden behind dust clouds or are too dim to detect individually. Our Sun is located in one of the spiral arms, specifically in a region called the Orion Spur or Orion Arm, which is actually a minor arm connecting two major spiral arms. We're approximately 26,000 light-years from the galactic center, about halfway between the center and the outer edge. This is considered a relatively safe, stable location. The galactic center is a chaotic, violent place with intense radiation and a supermassive black hole containing approximately 4 million times the mass of the Sunday. Being this far from the center is actually quite beneficial for life. The Milky Way isn't alone in space. It's part of a collection of galaxies called the Local Group, which contains approximately 80 galaxies spread across approximately 10 million light-years of space. Most of these galaxies are small dwarf galaxies, containing millions or billions of stars rather than hundreds of billions. The Local Group is dominated by two large spiral galaxies, our Milky Way and the Andromeda Galaxy. Andromeda, also called Messier 31 or M31, is approximately 2.5 million light-years away and is actually slightly larger than the Milky Way, containing roughly 1 trillion stars. It's the most distant object easily visible to the naked eye from Earth. On a clear, dark night, it appears as a faint, elongated smudge of light in the constellation Andromeda. Interestingly, Andromeda and the Milky Way are actually moving toward each other, not away. Gravity is pulling them together, and in approximately 4.5 billion years, they'll collide, and merge into a single, larger galaxy. This sounds catastrophic, but remember that galaxies are mostly empty space. The distances between individual stars are vast. During the collision, very few stars will actually hit each other directly. Instead, the two galaxies will pass through each other, their gravity disrupting each other's structure, pulling out long tails of stars, and eventually settling into a new configuration, probably an elliptical galaxy rather than a spiral. The Sun and Earth will probably survive this collision unscathed, though our night sky will look dramatically different as the two galaxies merge. Andromeda will fill a huge portion of the sky, and eventually the two galactic cores will merge, creating brilliant displays of new star formation visible across the merged galaxy. Of course, this is all billions of years in the future, and by that time, the Sun will have evolved into a red giant and consumed Earth, so humans won't be around to witness it, unless we've somehow migrated to other star systems by then. The nature of time across cosmic distances. One of the most philosophically interesting aspects of cosmic distances is what they mean for the nature of time. We tend to think of time as universal, as if there's a single now that extends throughout the entire universe. But relativity tells us this isn't true. There's no universal present moment. The concept of now is relative and depends on your frame of reference. For everyday life on Earth, this doesn't matter. The relativistic effects are too small to notice. When you talk to someone across the room, you're effectively communicating with them in the same present moment. The light delay between you is so tiny, measured in billionths of a second, that it's completely imperceptible. For all practical purposes, there's a shared now for everyone on Earth. But when we consider cosmic distances, this breaks down entirely. When you look at a star 100 light-years away, what does it mean to ask what's happening there right now? The question doesn't have a meaningful answer. You can see what was happening there 100 years ago, because that's when the light you're currently observing left the star. But there's no way to observe what's happening there now, in any absolute sense. The information simply hasn't reached you yet, and it won't reach you for another 100 years. Different observers moving at different speeds relative to that star would actually disagree about what now means at that star. Depending on your velocity and direction of motion, events that you consider to be happening now at that distant star could vary by days, years, or even centuries. This isn't because anyone's perception is wrong. It's because simultaneity itself, the concept of two events happening at the same time, is relative when the events are separated by large distances in space. This has profound implications for thinking about the universe as a whole. When we talk about the age of the universe being 13.8 billion years, we have to specify that this is measured in a particular reference frame, specifically the reference frame in which the cosmic microwave background radiation appears uniform in all directions. Observers moving at significant fractions of light speed relative to that frame would measure different ages, would have different experiences of cosmic time. In a very real sense, the concept of the universe having a single, universal time that applies everywhere is an illusion created by our limited perspective. We experience time flowing at a particular rate in our particular location and state of motion. Other observers elsewhere, moving differently, in different gravitational fields, would experience time differently. All of their perspectives are equally valid. There's no privileged reference frame, no universal clock ticking away the same seconds for everyone everywhere. The practical limits of space exploration. Given everything we've discussed about the vast distances involved, the finite speed of light, and the enormous energy requirements for interstellar travel, what are the realistic prospects for humanity exploring beyond our solar system? This is a question that scientists, engineers, and space enthusiasts have debated for decades, and there's no clear consensus answer. In the near term, within the next century or so, it seems likely that human exploration will remain confined to our solar system. We might establish permanent bases on the Moon or Mars. We might send crewed missions to the moons of Jupiter or Saturn, which are scientifically fascinating because some of them, like Europa and Enceladus, have subsurface oceans that might harbor life. We might mine asteroids for valuable resources. But leaving the solar system entirely, traveling to another star system, seems beyond our capabilities for the foreseeable future. The energy requirements are simply staggering. Remember, the fastest spacecraft we've ever built travels at less than 0.1% of light speed. To reach even a modest fraction of light speed, say 10%, would require overcoming enormous engineering challenges. You'd need a propulsion system far more powerful than anything that currently exists. You'd need to carry enough fuel, or have some other means of generating energy, to accelerate your spacecraft to that speed, and then decelerate again at your destination. Some scientists have proposed using nuclear fusion drives, which would be more efficient than chemical rockets and could theoretically achieve higher speeds. The challenge is that we haven't yet developed practical fusion reactors even for stationary power generation on Earth, let alone compact fusion drives for spacecraft. We've been working on fusion power for more than 70 years, and it remains stubbornly difficult to achieve in a controlled, sustainable way that produces more energy than it consumes. Another proposal is antimatter propulsion. When matter and antimatter meet, they annihilate each other and convert completely into energy, according to Einstein's famous equation, E equals mc squared. This is the most energy-dense reaction possible in physics. A tiny amount of antimatter could theoretically provide enormous amounts of energy for propulsion. The problem is that antimatter is incredibly difficult and expensive to produce. We can create it in particle accelerators, but only in microscopic quantities, and storing it is extremely challenging because it annihilates the moment it touches any normal matter. A more realistic, near-term approach might be something like Project Daedalus, a study conducted by the British Interstellar Society in the 1970s. They designed a theoretical spacecraft that would use fusion reactions to accelerate to approximately 12% of light speed. The spacecraft would be enormous, mostly fuel, and would be unmanned because the mission duration would be multiple decades, even to reach the nearest stars. It would be a one-way probe, unable to slow down or return, simply flying past its target at high speed while gathering data. Even this ambitious design, which pushed the boundaries of theoretical possibility, would take approximately 40 years to reach a star system 6 light-years away. And that's assuming we can solve all the technical challenges involved in building such a spacecraft, which would be far beyond anything we've ever constructed. The cost would be astronomical, likely requiring the combined resources of multiple nations over many years. Generation ships and the human factor. If we want to send actual humans to other star systems, the challenges become even more daunting. Unless we develop some kind of suspended animation or cryogenic freezing technology that allows people to sleep through decades or centuries of travel, any crewed mission to another star system would need to be a generation ship. A generation ship is a massive spacecraft designed to support a self-sustaining population for potentially hundreds or thousands of years. The people who begin the journey would not be the people who arrive at the destination. Multiple generations would be born, live, and die aboard the ship during the voyage. The arrival at the destination planet would be experienced by the distant descendants of the original crew. The engineering challenges of building such a ship are immense. You'd need to create a completely closed ecosystem that can sustain itself indefinitely without any external inputs. You'd need to recycle air, water, and nutrients with near-perfect efficiency. You'd need to grow food, probably through some combination of agriculture and aquaculture. You'd need to maintain complex machinery for hundreds of years in the harsh environment of space, where there's no possibility of obtaining spare parts or outside assistance. But the social and psychological challenges might be even more difficult than the engineering ones. How do you keep a population motivated and committed to a mission that will take generations to complete? The original crew volunteers for the mission, but their children didn't choose to be born on a spacecraft. Their grandchildren and great-grandchildren have even less connection to the original decision to embark on this journey. Would the mission maintain its social cohesion over centuries? Would people born in space who have never seen Earth or any planet, still feel committed to reaching the destination? Would they maintain the technical knowledge needed to operate and repair the ship? Would conflict and division arise? Would the population split into factions with different goals? Would some people decide they want to turn back, while others want to continue forward? These aren't idle questions. They're serious considerations that would need to be addressed before any generation ship could be built. History is full of examples of isolated communities developing in unexpected ways, diverging from their parent cultures, sometimes thriving and sometimes collapsing. A generation ship would be the ultimate isolated community, alone in the void of space, with no possibility of outside contact or assistance, for potentially hundreds of years. There's also the question of governance. What kind of political system would work for a generation ship? Democracy might be difficult if the population is relatively small, perhaps a few hundred or a few thousand people. Everyone would need to work together closely in a confined space for generations. Conflict or social breakdown could doom the entire mission. You'd need carefully thought out social structures, conflict resolution mechanisms, and ways to maintain morale and purpose over very long timescales. Some science fiction stories have explored the concept of generation ships, where the descendants eventually forget that they're on a ship at all. The journey takes so long that the original mission is forgotten, becoming myth or legend. The inhabitants think their ship is the entire universe. Eventually, when they arrive at their destination, it comes as a shock. They've lost the knowledge of how to land the ship or what to do when they arrive. It's a cautionary tale about the challenges of preserving knowledge and purpose across many generations. Alternative approaches to interstellar travel. Given the enormous challenges of sending humans to other star systems, some scientists have proposed alternatives that might be more feasible with near-future technology. One idea is to send tiny, lightweight probes instead of massive spacecraft. The less mass you need to accelerate, the easier and cheaper it is to reach high speeds. Project Breakthrough Starshot, announced in 2016 by physicist Stephen Hawking and billionaire Yuri Milner, proposes building thousands of tiny spacecraft about the size of a smartphone chip, weighing only a few grams each. These nanocrafts would have cameras, sensors, and communication equipment miniaturized to fit on a tiny chip. The innovative part of the proposal is how they'd be accelerated. Instead of carrying fuel, which would be too heavy, they'd be propelled by light. Each nanocraft would have an ultra-thin reflective sail. A powerful array of lasers on Earth would beam light at these sails, and the pressure of the light itself would accelerate the crafts to approximately 20% of light speed. At that speed, a nanocraft could reach Proxima Centauri in about 20 years. It would fly past the star system at high speed, taking photos and measurements, and beam the data back to Earth. The data would take another 4.24 years to reach us, so we'd receive results about 25 years after launch. That's ambitious, but potentially achievable within a few decades if the necessary technology can be developed and the significant funding challenges can be overcome. The challenges are still substantial. The laser array would need to be incredibly powerful, essentially creating a focused beam of light powerful enough to accelerate gram-scale objects to a significant fraction of light speed. The nanocrafts would need to survive 20 years of travel through interstellar space, enduring cosmic radiation and potential impacts with dust particles. Even a tiny speck of dust, impacting at 20% of light speed, carries enormous kinetic energy and could destroy the craft. The communication system would need to be powerful enough to send signals back across 4.24 light-years using only the energy available on a gram-scale spacecraft. And we'd need to launch many of these crafts, probably hundreds or thousands, because the odds of any individual craft surviving the journey intact are probably not very high. But if even a few succeed, they could send back humanity's first close-up images of another star system, which would be a monumental achievement. The search for extraterrestrial intelligence. Given that physical travel to other star systems is so difficult, another approach to connecting with potential alien civilizations is to listen for signals. This is the goal of SETI, the search for extraterrestrial intelligence, which has been ongoing in various forms since the 1960s. The idea is relatively simple. If there are advanced technological civilizations out there, they might be using radio waves or other electromagnetic radiation for communication, just as we do. Those signals would radiate out into space at the speed of light. If we point sensitive radio telescopes at the sky and listen carefully, we might detect artificial signals that indicate the presence of another civilization. Of course, radio waves travel at the speed of light, so there's still the distance problem. A signal from a civilization 100 light-years away would take 100 years to reach us. We'd be detecting a signal they sent a century ago. If we sent a reply, it would take another century to reach them. The total time for a back-and-forth exchange would be 200 years. That's not a conversation in any meaningful sense, but it would at least prove we're not alone. SETI researchers have been listening for decades, using increasingly sophisticated equipment and analyzing enormous amounts of data. So far, they've found nothing that's clearly an artificial signal from an extraterrestrial civilization. There have been a few interesting signals that initially looked promising, like the famous "wow" signal, detected in 1977, which was a strong, narrow-band radio signal that appeared to come from the direction of the constellation Sagittarius. But it was never detected again, and we have no idea what caused it. The lack of detection so far doesn't necessarily mean there's no one out there. Space is vast, and we've only searched a tiny fraction of it. There are hundreds of billions of stars in our galaxy, and we've only examined a few thousand of them in detail. It's like scooping a cup of water from the ocean, seeing no fish in it, and concluding there are no fish in the ocean. We simply haven't searched enough yet to draw firm conclusions. Moreover, we're making assumptions about what alien civilizations might do. We're assuming they use radio waves for communication, and that those signals are strong enough to detect across interstellar distances. We're assuming they're broadcasting at frequencies and times when we happen to be listening. We're assuming their technology is somewhat similar to ours. All of these assumptions might be wrong. An advanced civilization might use communication methods we haven't thought of or can't detect with current technology. The Drake equation and estimating alien civilizations. In 1961, astronomer Frank Drake proposed an equation to estimate the number of detectable alien civilizations in our galaxy. The Drake equation, as it's now called, breaks down the problem into several factors. The rate of star formation in our galaxy, the fraction of stars with planets, the number of planets per star system in the habitable zone, the fraction of those planets where life actually arises, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent species that develop technology detectable from space, and the length of time such civilizations remain detectable. Multiply all these factors together, and you get an estimate for the number of detectable civilizations. The problem is that we don't know most of these numbers with any certainty. We have reasonable estimates for the first few factors. We know the rate of star formation, and we've discovered thousands of exoplanets, giving us good statistics on how common planets are. But we have almost no data on the later factors. How common is life? How often does life evolve intelligence? How long do technological civilizations last? Depending on what values you plug into the Drake equation, you can get answers ranging from "we're the only civilization in the galaxy" to "there are millions of civilizations out there." Both extremes are possible given our current knowledge. We simply don't know enough to give a confident answer. Some of the factors are particularly uncertain and important. One is the lifetime of technological civilizations. How long does a typical civilization remain detectable before it either destroys itself, loses interest in broadcasting signals, evolves beyond radio communication, or otherwise becomes undetectable? If civilizations typically only broadcast for a few hundred years before moving on to other communication methods or destroying themselves, then even if civilizations arise frequently, there might be very few that exist at the same time we do. Think about human civilization. We've only been capable of sending radio signals into space for about 120 years, since the invention of radio in the late 1800s. and we're already moving toward more efficient, directed communication methods that don't broadcast strongly into space. If our pattern is typical, civilizations might only have a brief radio window of a few centuries where they're detectable using SETI methods. If the average civilization broadcasts for only 200 years, and civilizations are spread across our 100,000 light-year diameter galaxy, the chances of two civilizations' radio windows overlapping in time and them being close enough to detect each other are actually quite small, even if civilizations are relatively common. You'd have civilizations arising, broadcasting briefly, then going quiet or destroying themselves, scattered across space and time in a way that makes contact unlikely. The Great Filter Hypothesis. One particularly thought-provoking answer to the Fermi paradox is called the Great Filter. This hypothesis suggests that there's some extremely difficult evolutionary step, some barrier or filter, that prevents most potential life from progressing to become a spacefaring civilization. The question is, where is this filter in our evolutionary history? Maybe the filter is behind us. Maybe the hard step was the origin of life itself, or the evolution of complex cells, or the development of multicellular life, or the evolution of intelligence. If one of these early steps is extremely unlikely, then we might have already passed the Great Filter. We'd be incredibly rare, perhaps even unique, but we'd have reason to be optimistic about our future because we've already overcome the hard part. But maybe the filter is ahead of us. Maybe most civilizations destroy themselves shortly after developing advanced technology. Maybe nuclear war, environmental collapse, runaway artificial intelligence, or some other catastrophe tends to wipe out civilizations before they can spread to the stars. In this scenario, the reason we don't see alien civilizations is because they all died out, and we're likely to face the same fate. This is deeply unsettling to contemplate. If the Great Filter is ahead of us, then we're currently in the most dangerous period of human existence. We have the technology to destroy ourselves, but haven't yet developed the wisdom and social structures to prevent that destruction. The next few centuries might determine whether humanity joins the countless extinct civilizations scattered across the galaxy, or whether we become one of the rare species to pass through the filter and spread to the stars. We don't know which scenario is correct. The silence we observe when we look out at the cosmos could mean we're alone and precious, or it could mean we're doomed and just don't know it yet. Both possibilities are profound and troubling in their own ways. Light years and our cosmic perspective. Let's return to where we started, to the concept of a light year itself and what it means for our understanding of the universe. A light year is 9.46 trillion kilometers. It's the distance light travels in 1 year. It's a useful unit of measurement for cosmic distances because it makes the numbers manageable and because it directly connects distance with time in a meaningful way. When we say a star is 50 light years away, we're not just giving its distance. We're also telling you that the light you see from that star is 50 years old. We're explicitly connecting space and time, which are fundamentally linked according to relativity. Distance and time are not separate things but aspects of a single four-dimensional structure called space-time. The light year embodies this connection in a beautifully intuitive way. Understanding light years and the distances they represent fundamentally changes how you perceive your place in the cosmos. It makes you realize, in a visceral way, just how vast and ancient the universe is. It makes you understand that we're living on a tiny speck of rock orbiting an ordinary star in an ordinary galaxy, separated by unimaginable distances from everything else. This perspective can be humbling, even frightening. We're so small, so insignificant on cosmic scales. Everything that's ever happened in human history, every war fought, every empire built, every masterpiece created, every person who's ever lived and loved and died, all of it has happened on this one small planet, in a universe containing trillions of planets. From a cosmic perspective, we barely matter at all. We're like ants on a beach trying to comprehend the ocean, trying to understand something so much larger than ourselves that it defies comprehension. But this perspective can also be inspiring and even uplifting. We're tiny, yes, but we're also remarkable. We're matter that has organized itself in such a way that it can ponder the universe. We're the universe becoming aware of itself. Out of the chaos and randomness of cosmic evolution, somehow, through processes we're still trying to understand, consciousness emerged. Atoms arranged themselves into patterns complex enough to think, to wonder, to create, to love. We've existed for only the tiniest sliver of cosmic time. Modern humans have been around for approximately 200,000 years. Civilization has existed for perhaps 12,000 years. Recorded history spans only about 5,000 years. The entire span of human existence is less than 0.002% of the universe's 13.8 billion year history. We're newcomers, infants by cosmic standards. And yet, in that brief time, we've accomplished extraordinary things. We've figured out what stars are made of by analyzing their light. We've measured the age of the universe. We've detected gravitational waves from black holes colliding billions of light years away. We've landed robots on Mars and sent spacecraft to the outer solar system and beyond. We've taken pictures of the surface of Titan, Saturn's largest moon, showing us alien landscapes under an orange sky. We've detected thousands of planets orbiting distant stars, expanding our understanding of how common planetary systems are. We've decoded the structure of DNA and mapped the human genome. We've cured diseases that once killed millions. We've built machines that can think and learn. We've connected the entire planet through a communication network that lets people on opposite sides of Earth communicate instantly. We've created art, music, literature, and philosophy that explores the depths of human experience and imagination. All of this in just a few thousand years of civilization, a cosmic eye blink. What might we accomplish in the next 1,000 years if we survive? In the next million years? In the next billion years? The possibilities are staggering to contemplate. We might spread throughout the solar system, establishing permanent settlements on other worlds. We might develop new technologies we can barely imagine today. We might solve the mysteries of consciousness, of quantum mechanics, of dark matter and dark energy. We might even, eventually, find ways to reach other star systems despite the enormous challenges involved, perhaps through generation ships, or perhaps through technologies we haven't conceived of yet. Perhaps we'll develop suspended animation that allows people to sleep through centuries of travel. Perhaps we'll discover some loophole in the laws of physics that allows faster-than-light travel after all, though that seems increasingly unlikely the more we learn about relativity. Or perhaps we'll spread not as biological beings, but as information. Perhaps we'll develop artificial intelligence that can be transmitted as data at light speed, sent to other star systems and reconstructed there. Perhaps future humans will upload their consciousness into machines that don't age, don't require food or air, and can survive the harsh conditions of space travel for centuries or millennia. These ideas sound like science fiction, and they may remain forever fictional. But then again, much of what we take for granted today would have seemed like magic to people living just a few centuries ago. The responsibility of cosmic awareness. Understanding light years and cosmic distances carries with it a kind of responsibility. When you truly grasp how vast the universe is, and how rare and precious life appears to be, it changes how you think about our planet and our civilization. Earth is, as far as we know, the only place in the entire universe where life exists. It might be the only place where life has ever existed in billions of years and across trillions of planets. Or there might be other life-bearing worlds scattered throughout the cosmos, but they're so far away, separated by so many light years of empty space, that we'll never contact them or even know they exist. Either way, Earth is precious beyond measure. It's the only home we have, the only place we know of where the miracle of life has occurred. Every species on this planet, from bacteria to blue whales, represents billions of years of evolution, a chain of survival stretching back through countless generations to the very origin of life itself. When we drive species to extinction, we're not just losing individual organisms. We're ending entire branches of evolution that will never exist again. And human civilization, for all its flaws and problems, represents something equally precious. We're the only species we know of that can contemplate the universe, that can do science and mathematics, that can create art and music and literature. We're the only ones who can look up at the night sky and wonder what's out there, who can build telescopes to observe distant galaxies, who can send messages to the stars hoping someone might hear. If we destroy ourselves, through nuclear war or environmental collapse or any of the other existential risks we face, we might be extinguishing not just human life, but the only consciousness in this entire region of space. We might be silencing the only voice that speaks from this corner of the galaxy. The light from our sun would continue to shine for billions of years, but there would be no one here to observe it, no one to wonder about the cosmos, no one to carry forward the billion-year evolutionary experiment that produced consciousness. This doesn't mean we should be paralyzed by the weight of this responsibility, but it does mean we should take seriously the challenges we face as a civilization. Climate change, nuclear weapons, artificial intelligence, safety, biosecurity, asteroid impacts. These aren't just political issues or technical problems. They're existential challenges that could determine whether consciousness survives in this part of the universe. We're currently the only beings capable of defending Earth from asteroid impacts. If a large asteroid were heading toward Earth, we might be able to deflect it using rockets or other methods, but only if we see it coming and have time to act. We're the only species that can model climate systems and understand how our activities are changing the planet's environment. We're the only ones who can potentially prevent our own extinction through wisdom and foresight. In a very real sense, we're the universe's way of protecting itself, at least in this one small corner of space. We're the most complex and organized form of matter we know of, capable of understanding and influencing the world around us. With that capability comes responsibility, the poetry of light and distance. There's something deeply poetic about the fact that looking at distant objects means looking back in time. Every observation of the night sky is simultaneously a view across space and a view into history. The universe gives us a way to literally see the past, preserved in light that's been traveling for years, centuries, millennia, or billions of years. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago, when our ancestors were just beginning to diverge from other primates. The light you're seeing has been traveling through space longer than humans have existed as a distinct species. Some of the photons entering your eye might have passed within light years of other star systems, might have crossed the paths of comets and asteroids, might have witnessed cosmic events we'll never know about. When astronomers observe very distant galaxies, billions of light years away, they're seeing those galaxies as they were billions of years ago, when the universe was young. They're seeing ancient galaxies in the process of formation, witnessing events that happened before our solar system even existed. The light from those galaxies has been traveling for so long that it's been significantly stretched and redshifted by cosmic expansion during its journey. Some of the stars you see in the night sky might not even exist anymore. They might have exhausted their fuel and exploded as supernovae centuries or millennia ago, but because they're so far away, the light from that explosion hasn't reached us yet. For now, from our perspective, they still shine peacefully in the night sky. Their death is still in our future, even though it's already happened in their past. Time and space interweave in ways that challenge our intuitions about causality and existence. There's also profound beauty in the constancy of the speed of light. No matter where you are in the universe, no matter how fast you're moving, light always travels at the same speed relative to you. This constancy is one of the fundamental pillars on which modern physics is built. It's what leads to all the strange predictions of relativity, time dilation, length contraction, the equivalence of mass and energy. The speed of light is woven into the very fabric of space-time itself. It's not just a speed limit, but a fundamental property of the universe, as unchangeable as the rules of mathematics. Photons don't experience time at all because they're traveling at light speed. From a photon's perspective, If it could have a perspective, it's created and absorbed in the same instant, regardless of how many billions of years pass in our reference frame during its journey. The future of human understanding. We've come so far in our understanding of the universe, but there's still so much we don't know. Dark matter and dark energy remain mysterious. We don't know if the universe is finite or infinite. We don't know if there are other universes beyond our own, or if concepts like the multiverse are real, or just mathematical curiosities. We don't know what happened in the very first moments after the Big Bang, before the universe was even a second old. We don't know if life exists elsewhere in the universe. We don't know if consciousness is unique to Earth or common throughout the cosmos. We don't know if the laws of physics are the same everywhere in the universe or if they might vary in regions beyond our observation. We don't know the ultimate fate of the universe with certainty, though our best current models suggest it will expand forever, growing colder and emptier over trillions of years until even atoms themselves decay. But the fact that we can ask these questions, that we can formulate theories and test them against observations, is itself remarkable. We're using brains that evolved to help our ancestors find food and avoid predators on the African savanna, and we're applying those brains to understand the structure of reality itself. It's audacious, almost absurd, and yet it's working. Every generation builds on the knowledge of previous generations, advancing our understanding incrementally. Copernicus showed that Earth orbits the Sun, not the other way around. Galileo used the first telescopes to observe Jupiter's moons and the phases of Venus, providing evidence for the heliocentric model. Newton developed laws of motion and gravity that could predict planetary orbits with precision. Einstein showed that space and time are flexible and interconnected, that gravity is the curvature of space-time itself. Hubble discovered that the universe is expanding, fundamentally changing our understanding of cosmic history. Hawking and Penrose proved theorems about black holes and the nature of space-time singularities. Countless other scientists, many of whose names are known only to specialists in their fields, have each contributed pieces to the puzzle, advancing human knowledge bit by bit, measurement by measurement, insight by insight. The process continues today. Observatories like the James Webb Space Telescope, launched in late 2021, are providing unprecedented views of the early universe, showing us galaxies that formed when the cosmos was only a few 100 million years old. Gravitational wave detectors like LIGO and Virgo are opening an entirely new window on the universe, allowing us to observe cosmic events through ripples in space-time rather than through light. Particle accelerators are probing the fundamental constituents of matter, searching for new particles and forces that might extend our understanding beyond the standard model of particle physics. Quantum computers are being developed that might one day solve problems that are completely intractable for classical computers. Artificial intelligence systems are helping scientists analyze vast quantities of data, finding patterns that human researchers might miss. We're living in an extraordinary time for science and discovery. More is being learned about the universe now, in these early decades of the 21st century, than in any comparable period in human history. And yet, despite all this progress, we've barely scratched the surface of what there is to know. The universe is vast beyond comprehension, and our exploration of it has only just begun. The legacy we leave. Understanding light years and cosmic distances isn't just about science and astronomy. It's about perspective, about understanding our place in the grand scheme of things. It's about recognizing both our insignificance and our significance simultaneously. We're insignificant in terms of size and duration. We're tiny creatures on a tiny planet, orbiting an ordinary star in an ordinary galaxy, living for mere decades in a universe billions of years old. If humanity disappeared tomorrow, the universe would continue on, completely unchanged. The stars would keep shining, galaxies would keep colliding and merging, black holes would keep devouring matter, and the expansion of space would continue accelerating. Our absence wouldn't matter at all on cosmic scales, but we're significant in terms of meaning and consciousness. We're the ones who observe, who understand, who care. The universe might be vast and ancient, But without consciousness, without observers to perceive it, and minds to comprehend it, it's just matter and energy, following the laws of physics mindlessly. Consciousness, wherever it exists, transforms the universe from a mechanical process into something with meaning and purpose. We create meaning through our choices and actions. We determine what kind of civilization we want to build, what values we want to uphold, how we want to treat each other and the planet we inhabit. We decide whether to pursue knowledge and exploration or to turn inward and stagnate. We choose whether to work together to solve global challenges or to let tribal conflicts and short-term thinking doom us to extinction. The choices we make in the next few centuries will likely determine humanity's long-term future. Will we spread beyond Earth and establish ourselves as a multiplanetary species, ensuring our survival even if disaster strikes our home planet? Or will we remain confined to Earth, vulnerable to extinction from asteroid impacts, supervolcanic eruptions, or disasters of our own making? Will we solve the technical challenges of interstellar travel and eventually reach other star systems, carrying the light of consciousness across the light years to other worlds? Or will the distances prove forever insurmountable, leaving us isolated in our solar system, alone with our thoughts in a vast and unreachable cosmos? Will we find evidence of life elsewhere in the universe, or will we gradually come to accept that we might be alone, the only voices speaking into the cosmic void? Will we grow wiser as a species, developing the social and political structures needed to prevent self-destruction? Or will we succumb to the same fate that might have claimed countless other civilizations throughout the galaxy? These questions don't have predetermined answers. The future is not fixed. It depends on choices that haven't been made yet, on actions that will be taken by people who aren't even born yet. Every generation inherits the world created by previous generations and has the responsibility to leave something better for future generations. Our cosmic childhood. From a cosmic perspective, humanity is in its infancy. We're only just beginning to understand the universe and our place in it. We've only recently developed technology that allows us to leave our planet's surface. We've only been studying the cosmos scientifically for a few centuries. We're cosmic children, just beginning to open our eyes and look around, just starting to ask the big questions about existence and meaning. Like all children, we make mistakes. We fight among ourselves. We damage things without fully understanding the consequences. We're impulsive and short-sighted at times. But also like children, we're curious and creative and full of potential. We're learning and growing. Each generation understands a little more than the previous generation did. Perhaps one day, if we survive and continue to advance, we'll look back on this era as a kind of cosmic childhood. Future humans, living in settlements throughout the solar system or even beyond, will remember that there was a time when all of humanity lived on a single planet, when we didn't yet understand the basic structure of reality, when we were just beginning to explore and wonder about the cosmos. They might look back with the same mixture of fondness and embarrassment that adults feel when remembering their childhood. They'll see our mistakes clearly, all the things we did wrong, all the suffering we could have prevented if we'd been wiser. But they might also appreciate the courage and curiosity of these early generations who took the first steps into space, who asked the first scientific questions, who began the long journey toward understanding. Standing under the night sky. The next time you're outside on a clear night, far from city lights, take a moment to look up at the stars. Really look at them. Don't just glance up and move on. Stop and observe for a while. Let your eyes adjust to the darkness. Watch as more and more stars gradually become visible, as your pupils dilate and your visual system becomes more sensitive. Think about what you're seeing. Every point of light is a sun, many of them far larger and brighter than our own. The light entering your eyes left those stars years, decades, or centuries ago. You're literally seeing into the past, observing ancient light that's been traveling through the void of space for longer than you've been alive. Think about the distances involved. The nearest stars are over 4 light-years away, roughly 40 trillion kilometers of empty space. The most distant stars you can see with your naked eye are thousands of light years away, and those are just the nearby ones, the tiniest fraction of our galaxy. The vast majority of the Milky Way's hundreds of billions of stars are completely invisible to you, hidden by distance and the limitations of human vision. And the Milky Way itself is just one galaxy among hundreds of billions or trillions in the observable universe. Each of those galaxies contains billions or trillions of stars. Each of those stars might have planets. The scale is so enormous that it defies comprehension. Your mind simply can't hold it all at once. And yet, here you are, standing on the surface of one of those planets, looking up at it all. You're made of atoms that were forged in the cores of ancient stars that exploded billions of years ago, scattering their enriched material into space, where it eventually coalesced into new stars and planets. You're literally made of stardust, and now you're looking back at your cosmic origins. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon that forms the backbone of every molecule in your body, all of it was created in stellar furnaces and supernova explosions. You're not separate from the cosmos. You're part of it. You're the universe observing itself, matter organized in such a way that it has become conscious and curious. The final reflection. A light year is 9.46 trillion kilometers. It's the distance light travels in 1 year of continuous motion at 300,000 kilometers per second. It's a measurement we need because the universe is so incomprehensibly vast that our everyday units of distance become meaningless when applied to cosmic scales. Understanding what a light year represents, truly grasping the distances involved, and what they mean for our ability to explore and comprehend the cosmos, is both humbling and inspiring. It shows us that we're incredibly small, living on a tiny planet in an unimaginably vast universe. But it also shows us that we're remarkable, capable of measuring and understanding distances our ancestors couldn't even conceive of, capable of asking deep questions about existence and meaning. We're alone on our small planet, separated from everything else by light years of empty space. The stars we see in the night sky are unreachably distant. The galaxies beyond are even more remote. If there are other civilizations out there, other conscious beings looking up at their own night skies and wondering if they're alone, we may never know about them. The distances are simply too great, the journey too long, the obstacles too formidable. And yet, we keep looking, we keep wondering, we keep building better telescopes, sending out messages, listening for signals, pushing the boundaries of what's possible. Because that's what consciousness does. It explores, it questions, it seeks to understand. Even if the answers are difficult or disturbing, even if the truth shows us that we're small and isolated, we still want to know. This drive to understand, this curiosity about the cosmos and our place in it, might be one of the most fundamentally human traits we possess. For thousands of years, humans have looked up at the night sky and wondered what those points of light are, where they came from, what they mean. We've created myths and stories to explain them. We've built monuments aligned with celestial events. We've navigated across oceans using the stars as guides. And now, in the last few centuries, we've begun to actually understand what we're looking at. We've measured the distances to the stars. We've determined their composition, their age, their fate. We've discovered that the universe has a history, that it had a beginning and will have an end. We've found that we're not at the center of anything special, just inhabitants of one planet among countless others. This knowledge doesn't diminish us. If anything, it elevates us. We're small, yes, but we figured out our smallness. We're brief, yes, but we've measured the age of the cosmos. We're insignificant on cosmic scales, yes, but we're the only beings we know of who can make that judgment. Every time you look up at the night sky, you're participating in this ancient human tradition of cosmic wonder. You're looking at the same stars and planets that countless generations before you have observed. The constellations you see are the same ones that ancient humans saw thousands of years ago. The Milky Way, stretching across the sky, has been visible to humans for as long as humans have existed. But you know things about what you're seeing that those ancient observers didn't. You know that the Milky Way is a galaxy containing hundreds of billions of stars. You know that the planets wandering against the background stars are worlds like Earth, some with moons of their own, some with rings, each one a unique environment shaped by billions of years of cosmic evolution. You know that the stars are distant suns, that the distances between them are measured in light years, that the light you're seeing is ancient, showing you the universe as it was in the past. This knowledge is precious. It's been hard-won through centuries of careful observation, mathematical analysis, and scientific reasoning. It's one of humanity's greatest collective achievements, built by thousands of scientists and thinkers across many generations and cultures. It's a legacy that's been passed down to you, a gift from all the curious humans who came before. Conclusion: a light year represents more than just distance. It represents the fundamental structure of our universe, where space and time are intertwined, where information travels at a finite speed, where the cosmos is so vast that even light needs years, centuries, or billions of years to cross it. It represents both the incredible scale of creation and the limitations we face in exploring it. Understanding light years changes how you see the universe. It makes you realize that when you look at the night sky, you're not just seeing distant objects. You're seeing into the past, observing ancient light from events that happened before you were born, sometimes long before humans existed. You're witnessing the universe's history written in light, a cosmic record of events scattered across billions of years. It makes you appreciate how special our situation is. We're on a planet with liquid water, a protective atmosphere, and a stable star that will shine for billions of years. We're in a relatively quiet region of our galaxy, far from the chaotic center and the intense radiation that would make life difficult or impossible. We've existed during an era when the universe is old enough to have formed complex chemistry and stable planetary systems, but young enough that stars still shine brightly and galaxies haven't yet dispersed into isolation. We're cosmically fortunate to exist at all, in a place and time where consciousness can arise and flourish, and we're using that consciousness to understand the very cosmos that created us. We're measuring light years, calculating cosmic distances, determining the age and fate of the universe, searching for meaning in a vast and ancient cosmos that existed long before us and will continue long after we're gone. This is what a light year means. It's not just a number or a unit of measurement. It's a window into the true nature of reality, a tool for understanding our cosmic context, a reminder of both our insignificance and our importance. It shows us that the universe is larger, older, and stranger than we ever imagined, and that we're incredibly fortunate to be here, in this moment, able to observe it and wonder about it. So the next time someone mentions that a star is 10 light years away, or a galaxy is 2 million light years distant, you'll understand what that really means. You'll grasp the enormous distances involved, the ancient light carrying information across the void, the fundamental limitations imposed by the speed of light, and the remarkable achievement of human curiosity that allows us to measure and comprehend these cosmic scales. And perhaps you'll feel what I feel when I contemplate these distances. A mixture of humility at our cosmic insignificance and pride at our intellectual achievements. A sense of loneliness at our isolation, combined with wonder at the beauty and complexity of the universe. And above all, gratitude for the opportunity to exist in this cosmos and to understand, even briefly and imperfectly, the magnificent reality in which we find ourselves. Thank you for joining me on this journey across the light years. Keep looking up, keep wondering, and never stop asking questions about this remarkable universe we call home.